Hello everyone, welcome to this lecture series in Differential Calculus. Today we are going to talk about limit and continuity of a function of two variables. We have already talked about this concept for one variable, and today we are going to extend it for multivariables, that means for two variables. So first is the definition of limit for function of two variables. We say that a function fxy approaches the limit L as xy approaches x naught y naught, and we write limit xy approaching x naught y naught fxy equals L. So this is the very intuitive way of writing the limit, that the function will approach L as the xy approaches the point x naught y naught. Okay, or we can say that the function lies arbitrarily close to L whenever the points x y are sufficiently close to the point x naught y naught. Okay, so but how close the uh, points x y lie to x naught y naught so that the function is lie arbitrarily close to L? That in that context, this can be extended as a formal definition, that if for every epsilon positive there exists a corresponding delta positive, such that for all xy in the domain of function, the function lies close to L whenever xy lies sufficiently close to x naught y naught. Okay, so how much close function lies to L is within the epsilon distance. Okay, and how much close is xy to the point x naught y naught is within the delta distance. Okay, so see here that this modulus means the distance of function from L, and this modulus is less than epsilon means function lies within the epsilon distance from the L. Okay, so if this is your L point, then this function marked here lies within this distance is less than the epsilon distance from the point L. Okay, so this is L minus epsilon and this is L plus epsilon. Okay, so this is the epsilon distance on both sides. So function lies within the epsilon distance from L, and here the left inequality makes sure that the xy point is not equal to x naught y naught. Okay, and the right inequality says that uh, x minus x naught square plus y minus y naught square is less than delta square. Okay, so that means the points xy lies in the neighborhood of x naught y naught, and that neighborhood is a disk centered at x naught y naught of radius delta. Okay, so if at x naught y naught if there is a disk of radius delta, then for all xy points which lie within that disk, okay, so whenever the points xy lie within the delta distance from the x naught y naught. Okay, so in one variable, if you remember, then there is only left and right hand limit. Okay, but now the domain is the xy plane. Okay, and if you have a domain in the xy plane, then for any point x naught y naught in that domain, the neighborhood points can be on any direction. Okay, not just the left and right direction, but it can be on any direction in the xy plane. So the neighborhood here is not an interval, but it's a disk. Okay, and so for every point or any point lying in the neighborhood of x naught y naught which lie within the delta distance, okay, the corresponding function lies within the epsilon distance. If this is true, then we say that the function is arbitrarily close to L whenever this holds. That means xy lies sufficiently close to the point x naught y naught. Okay, so in one variable also we have already discussed the steps on how we can solve and find the relation between delta and epsilon. Okay, so we used to solve this epsilon inequality first, and then we try to figure out what should be the value of delta corresponding to each epsilon, so that both these inequalities are satisfied. Okay, so if you can find that relation, then you can say that this limit will hold. Okay, and this definition applies to the interior points of the domain as well as the boundary points of the domain, although the boundary need not lie within the domain. Okay, and so this definition is based on the Cartesian coordinates. In case if you are solving the epsilon inequality and trying to find this delta, and you cannot make sufficient progress in this, then you can also think about changing it to polar coordinate system. Okay, so like if I put x minus x naught as r cos theta and y minus y naught as r sin theta, then you can see that this inequality reduces to r less than delta. Okay, and on this side it will be a function of r cos theta, r sin theta. Okay, so this limit will reduce to limit on r. Okay, right. So we can also try and solve in polar coordinates, but we have to be very careful if whenever we use polar coordinate system. Okay, so let us take, say, uh, see first that how many paths exist when we talk about functions of two variables. As we know that when we talk about function of one variable, then if we say that the limit at the interior point x is equal to c, if we want to check, then we say that if both left and right hand limit exist and equal to one another, then this holds. Okay, then the limit at x is equal to c holds. So for a function of one variable, we only try to check the left hand limit and the right hand limit, and if they both are equal, then we say that limit exists at that point. But in case of function of two variables, okay, we can approach the point from infinitely many points, directions. Okay, so when dealing with two variable functions, we can approach any point a b from more than two directions. In fact, we can approach this point from infinitely many directions. As you can see, say this is the point a b, and this is the disk of delta distance. Then for any point in the neighborhood, you can approach using a straight line, or you can approach using a parabolic line, or you can approach by an arbitrary curve. Okay, so there are infinitely many possible paths that are straight, curved, and in varying directions. Okay, so we cannot just use the left hand right hand limit and say limit exists. We have there are infinitely many different directions and paths by which you can approach that point a b from the neighborhood point xy. Okay, so uh, we can utilize epsilon delta definition to prove the limit, if limit exists, or otherwise if limit do not exist at a point, then because there are infinitely many paths, and we know that if limit exists, it should be unique for every path. So for limit do not exist at a point, we then there should be at least two paths for which we get two different limit values. Okay, so there is a two path test for non-existence of a limit at a point. Okay, so if a function fxy has different limits along two different paths in the domain of function as xy approaches x naught y naught, then we say that the limit of function as xy approaches x naught y naught does not exist. Okay, so if you can find a path or and a second path such that the limit along these two different paths is different, then we immediately say that limit do not exist at the point. Okay, so now if we have to prove the limit, then you can utilize the epsilon delta definition and prove that limit holds. Or if you want to prove that the limit do not exist at a point, then you just need to find out two different paths which give two different limit values, and because limit has to be unique, then we can say that limit do not exist at a point. Okay, so before we take a definition, I just add one result based on the algebraic properties of the limit of function of two variables, that the following rules hold if L, M and K are real numbers, and if we know the limit of function f as L as xy approaching x naught y naught, and limit of function g is m when xy approaching x naught y naught, then the following properties hold, and these we already did for a single variable, and the first rule is the sum rule. Okay, so if you know that the limit of f is L and limit of g is m as xy approaches x naught y naught, then the limit of their sum is simply L plus m. Okay, similarly we did other rules like difference rule, that the limit of difference of two functions, if you know the limit of individual as Lm, then their difference limit is L minus m. The constant multiple rule. Okay, so the limit xy approaching x naught y naught on k times function is k times L. Okay, where k is any number provided we know the limit of function f as L. Okay, fourth is the product rule, that limit of function f into g as xy approaching x naught y naught is L into m. Okay, where L is the limit of f and m is the limit of g. Okay, so limit of product is product of limits. Okay, quotient rule, that limit of quotient of functions f by g is L by m provided the limit of denominator is non-zero. Okay, so m has to be non-zero. Then the sixth is the power rule, that the limit of function power n is L power n, where n is a positive integer. Okay, and the root rule, that the limit on nth root of function is nth root of L, where L is the limit of function, and if n is even, then we assume L to be positive for this to exist. Okay, so these are all rules we did for one variable. The same holds for two variable functions. Okay, and so if you know the limit of f and g, then you can manipulate to find the limits of their sum, difference, product, and so on. Okay, so now I turn to one example where we have to find the limit of a function at origin if it exists. Okay, so function is 4x y square over x square plus y square, and when xy approaches origin, what happens to the limit of this function. Okay, to start with, you can see that the domain of the function is all xy points except the origin. Okay, so and we have to check the limit as xy approaching the origin 0 0. Okay, so intuitively, if you look at the limit value, okay, so the possible value of limit is taken 0 here. Okay, by noting one path, which is a vertical path. Okay, so when uh, x is 0 and y is non-zero, so that's the vertical part along the y-axis if we approach the origin. So any point on the y-axis other than origin, if you take, so at that point y will be non-zero and x will be 0. Okay, so if I use that path, then numerator will become 0 and denominator is y square. Okay, so it will be 4 by y, 0 by y square, and when y approaches 0, because it is already 0, so limit value must be 0. Okay, so by that path L is 0. Okay, so if limit do exist, then limit should be 0, because limit has to be unique. Okay, so by definition we have to prove that for epsilon positive given arbitrarily, we have to find a delta positive such that the function minus the limit, and limit is 0. Okay, by we have checked on by one path. Okay, so function minus limit modulus less than epsilon whenever 0 less than root of x square plus y square less than delta. Okay, so x naught y naught is 0 0, so x minus x naught square plus y minus y naught square immediately reduced to this x square plus y square. Okay, so that means uh, whenever for all xy point which lie in the disk centered at origin and radius delta. Okay, if xy points approaches origin, then this modulus must be less than epsilon to for limit to exist. So we know from single variable that we solve this by solving the epsilon inequality first, and then we try to find out if there is any delta possible corresponding to each epsilon. Okay, if it is true, then we can say that the limit exists. So we'll solve this left hand side, that the modulus of 4xy square over x square plus y square. Okay. And since the y square is always less than equal to x square plus y square, okay, for any xy, okay, uh, so this left hand side can be written as uh, 4 times modulus x so into y square over x square plus y square, okay, because square is a positive quantity, and because of this inequality y square over x square plus y square is less than equal to 1. So this whole quantity is less than equal to 4 times modulus of x, okay, and modulus of x is equal to root of x square, and x square is less than x square plus y square, just like y square is less than equal to x square plus y square. Similarly, x square is also less than equal to x square plus y square. So we can say that this inequality we can use x square is less than equal to x square plus y square. Okay, so this modulus is less than equal to 4 times root of x square plus y square, and root of x square plus y square is less than delta. Okay, so this will be like 4 delta. Okay, so if I choose 4 delta to be epsilon or delta to be epsilon by 4, then both these conditions will be automatically satisfied. Okay, so if we choose delta to be epsilon by 4 and let that this is true, then this is less than epsilon, okay, by this inequality. Okay, because this is 4 less will be less than 4 delta and delta is epsilon by 4. Okay, so both these inequalities will hold simultaneously, and limit of xy tending to 0 0 on this must be 0. Okay, so result holds true. Okay, so this is by definition epsilon delta definition, that the limit exists and it is equal to 0. Okay, so as I said earlier, that we can also solve using the polar coordinates. Okay, so in this case, for example, if you use x is equal to r cos theta, y is equal to r sin theta, then this result will be like r less than delta. Okay, and here if you put x as r cos theta and y as r sin theta, and then this denominator will be r square. Okay, so this whole quantity will reduce to 4 times r times cos theta times sine square theta modulus. Okay, and then that will be less than equal to 4 times r, because cosine theta and sine theta, their modulus is less than equal to 1. Okay, so this modulus will be reduced immediately to 4 times r. Okay, and r is less than delta, so the same situation this will arise. Okay, this will be 4r less than delta, so again delta equal to epsilon by 4 if we choose. Then in polar coordinates also we can prove that this whole result is true. Okay, now we take one more example here, that if a function is y by x, uh, does limit xy tends to 0 0 on function exist or not. Okay, so again if you note that the domain of the function is all xy points on the plane except where denominator is 0. Okay, so all points on the xy plane except x0. Okay, so x cannot be equal to 0. So basically when x non-zero means the points on the y-axis are not in the domain. Okay, so the domain of the function does not include the y-axis. Okay, so we do not consider any points x, y where x equals 0 in the approach towards the origin. Okay, so we have to find the limit approaching origin. Okay, so we will not move along the y-axis. Okay, so we, because when we find calculate limit, then we must take only points which are in the domain. Okay, so all the paths where paths only move along the domain. Okay, so along the x-axis, okay, uh, the value of the function f of x0 on the x-axis points are of the form x comma 0. Okay, so the function value x comma 0 immediately gives you 0. Okay, for all x non-zero. Okay, so if you take any point on the x-axis, the function value is exactly 0. Okay, so if the limit does exist when xy approaches 0 0, okay, so if we move along the x-axis towards the origin, the limit value must be 0 because function values are 0 on the x-axis. Okay. Now on the other hand, uh, along the y equal to x line, okay, so if you move along this line y is equal to x, the value of the function is on y is equal to x is x by x, because y substituted x is equal to 1 for all x non-zero. Okay, so if we move along the line y is equal to x towards origin, because function is everywhere 1, we the value of the limit should be 1 along that line. Okay, so there are two different paths along which we are getting two different limit values. Okay, this means that for every disk of radius delta, if we construct with center at origin, the disk will contain points of the form this x0 on the x-axis where value of function is 0, and also of the form x comma x along the line y equal to x where the value of the function is 1. Okay, so uh, along two different paths, we are getting two different limit values. So by the two path test we can say that the limit do not exist. Okay, so this limit do not exist as xy approaches origin. Okay, so now as I said, we have to just try and look at to find two different paths. Okay, so this is one way. uh, the other way is that if you can substitute y as an function of x or x as a function of y, such that the limit, say if I substitute y as a function of x, and if I take then the limit x approaching origin, because we have to move to origin in this case, and then if the limit values are not unique, then immediately you can say that the limit will not exist. For example, in this case, if I move along any straight line, if I put y as mx, okay, so if I move along any straight line to origin with different slopes m, then you will see that if I put y is equal to mx, then x will cancel out before any neighborhood point. Okay, so the function values are m. So when xy approaches origin, the function value is m. For different slopes I'm getting different limit values, and so limit does not exist in this case. Okay, say I take one more example here to show or prove this, that how we can choose this function. Say show that the function fxy equal to 2x square y over x4 plus y square has no limit as xy approaches origin. So we have to show that the limit do not exist as the points tend to origin. Okay, so can you show some paths for which the limit value will be different, or can you construct a function y of x, okay, such that the x cancels out in the numerator and denominator. Okay, so in this case you see that if I choose y to be uh, equal to mx square, okay, so parabolic paths y is equal to mx square. So if I put y is equal to mx square here, then the total power of x in the numerator will be 4, and y is equal to mx square will make this x power 4. So x power 4 will cancel out, and it will be function value will be a function of m. So for different m values I will get different function limits. Okay, so immediately we can prove that the limit do not exist by two path test. Okay, so that's what we are going to do it here. Okay, the limit cannot be found by direct substitution because it's a 0 by 0 form. Okay, so we examine the function along different paths, and one of the important path here is the parabolic curve. Okay, that end at origin. Okay, so we substitute, say y is equal to kx square for x non-zero. Okay, so why this substitution? Because it will end up with different k values, it will end up giving different limit values. Okay, so if I put y is equal to kx square here, then the function value at y is equal to kx square, if I put y is equal to kx square, you see that it is this. And so the for x non-zero I can cancel out x, so it will be only equal to 2k over 1 plus k square. Okay, so when y is substituted in terms of x, so it is a function of x only, and so when limit x goes to 0, okay, so when we approach origin, then this value remains 2k over 1 plus k square. Okay, so for different values of k, so along when k is 1, y is equal to x square path, okay, it gives some value. When k is 2, y is equal to 2x square path, it gives a different value, and so on. So for different k it is giving a different limit value. Okay, so by two part test the function has no limit as xy approaches origin. Okay. So we can prove that limit do not exist by showing two different paths for which function limit value is different. Okay. The next definition is the continuity of a function of two variables, and if you remember that a function fxy is said to be continuous at the point x naught y naught if the function is defined at that point. Okay, so function value at x naught y naught is there, and the limit xy tends to x naught y naught on function exists. Okay, so limit of function exists. And third is that the limit of function must be equal to the function value at that point. So if all these three conditions are met, then we say that function is continuous at the point x naught y naught. And if a function is continuous at every point, then we say that the function is continuous in its domain. Uh, so we can also write this in terms of epsilon delta inequality, that for because this is a limit equal to function, so this value is nothing but the L value. And so for the formal definition of continuity as in one variable, now to extend it to two variables, we can write that for every epsilon positive there exists a delta positive such that the modulus of function uh, from f minus f at x naught y naught, this must be less than epsilon whenever uh, the points x y lies in the inside the disk of delta distance from the center x naught y naught. Okay, so 0 less than square root of x minus x naught square plus y minus y naught square less than delta. Okay, so this definition. Okay, say for example show that this function is continuous at every point except at origin. Okay, so for points other than origin, it is simple that whenever xy is not equal to origin, okay, then function value is this 2xy over x square plus y square. Okay, so it's a polynomial by polynomial. And for non-zero points, okay, this polynomial has a limit and this polynomial also has a limit. So by algebraic property, if this is g function, this is h function, and it has a limit, it has a limit, then g by h also has a limit, and so is their continuity. Okay, so the function is continuous at every point non-zero because its values are then given by rational function of x and y. Okay, and limiting value is obtained by substituting x and y into the function expression. Okay, so there is no problem. Now at origin, because if this is not given, then 0 was not in domain, but now 0 is in the domain because specifically at origin the function value is defined as 0. Okay, so we just need to check what happens to the limit when xy approaches origin. Okay, when xy approaches origin, that means xy are not 0 0, so this is the function. Okay, so and for continuity the limit value must be 0. Okay, so here we can see that there is a path of straight lines along which the function can give different values. Like if I put y is equal to m times x, then you can see your numerator will be x square and denominator will be both terms x square, so x square will cancel out and it will be a function of m only. Okay, so along the curve y is equal to mx, when x is non-zero, the function along this path for any m uh, gives us that it is 2m over 1 plus m square. The x square will cancel out because x is a non-zero quantity. Okay, and so limit xy tends to 0 0 on this function remains 2m over 1 plus m square, and so limit is not unique. Okay, so different paths gives different values. Okay, so y is equal to x when m is 1, will give one value, y m is equal to 2, so y is equal to 2x straight line will give the different value, okay, and so on. So the limit do not exist, and if the limit do not exist, function cannot be continuous at origin, okay. So this was our concept of limit and continuity of two variables. In the next lecture we'll talk about the partial derivatives of function of two variables. Okay, have a very good day.